Okay, folks, we're into our final unit here. So we're going to start in, this unit is over mathematical modeling. So you've probably been seeing a lot of different mathematical models in the news recently. So it's pretty timely. Today we're going to talk about linear versus exponential growth. So you've probably actually been seeing a lot of exponential graphs like this green one lately, just because in epidemiology, the study of the spread of diseases, that's kind of the way they tend to spread exponentially at first, but then they'll drop off and become more logistic curves, meaning you're going to see a taper off eventually, right? All right, so let's talk about the difference between exponential and linear growth. So linear growth occurs when a quantity grows by the same absolute amount in each unit of time, and exponential growth occurs when a quantity grows by the same relative amount, meaning the same percentage in each unit of time. So the consequences of that in terms of growth are this. Here, the Power Town graph is exponential growth, and the Straight Town, the blue graph, is linear growth. You can see that exponential growth doubles at a much faster rate than linear growth. All right, so I'm going to give you a couple examples of situations, and we're going to decide whether it's the growth or decay is linear or exponential, and then we'll answer the associated questions. So the number of students at Wilson High School has increased by 50 in each of the past 4 years. What is the student population? If the student population was 754 years ago, what is it today? So in this case, we would just take that initial amount, 750, and we would keep adding the same absolute amount of 50 students each year. So 50 the first year, 50 the second year, 50 the third year, and 50 the fourth year. And so the thing I want you to notice about that is we can do that much more quickly just by going 750 plus 50 times the number of years that we want to see the growth for. So times 4, which is 750 plus 200, or 950 students. And so this is linear growth. So it's called linear because hopefully you notice that when I figured it out this way, it looks a lot like a linear equation, right? Which was the mx plus b model. But in our case, that kind of corresponds to 50 times the number of years plus the initial amount, 750. So it's called linear because it translates to a linear equation. All right, B, the price of milk has been rising at 3% per year. What is the price of a gallon of milk if it was $4 a year ago today? This is exponential growth. And the reason we know that is because they gave us a percent it's rising over a unit of time, so 3% per year. So the way I would figure this out is I would take the price that it was, which was $4 a year ago, and I'm going to multiply it by 1.03, meaning it's increasing by 3%. So if I just multiplied it by 0.03, that would tell me what 3% of $4 was, and then I would have to add that back on to the original $4. But here, taking the $4, I'm saying it's going to cost 100% of the $4 plus an additional 3%. So that does it all in one calculation. We can just pop that into our calculator. And we get that it costs now $4.12. Okay, Tax law allows you to depreciate the value of your equipment by $200 per year. If you purchased the equipment 3 years ago for $1,000, what its depreciated value today? Again, they're giving us an absolute amount of decay here, so this is linear decay. And we're just going to create a linear function to figure this out. So it started out as $1,000, and we're allowed to depreciate it by $200 per year. So minus $200 times the number of years. So for us, that's 1,000 minus 200 times 3 years. Whoops, 1,000. So that's 1,000 minus 600, or it's worth $400 today. And again, that's linear decay. The memory capacity of the state-of-the-art computer storage devices is doubling approximately every 2 years. If a company's top-of-the-line drive holds 16 terabytes today, what will it hold in 6 years? So this one is exponential growth. And the reason I know that is because they give us its doubling time over a unit of time. It's doubling every 2 years. So that means it's growing by 100% every 2 years. So what will it hold in 6 years? Well, that means it will double. So doubles 3 times, right? Because it doubles every 2 years. So if it holds 16 terabytes today, it's going to double once, then that's going to double, then that's going to double. So this is called exponential growth, we can see, because I can rewrite this as an exponential equation, right? So this is, that's 2 to the third. And so what I really have is 16 terabytes times 2 to the third, which is 128 terabytes. All right, the price of a high-definition TV set has been falling by 25% per year. If the price is $1,000 today, what could you expect it to be in 2 years? So here, they're giving us its relative decay over a unit of time. So we're going to call this exponential decay. The way I want to think about it is if it is dropping by about 25% per year, that means it's worth about 75% of its prior year's value. All right, so if it starts off costing $1,000, so it starts off costing $1,000, and then after 1 year, it's going to be worth 75% of that. And then after another year, it's going to be worth 75% of that. So this is 1,000 times 0.75 squared, which is an exponential expression. So 1,000 times 0.75 squared, it's going to be worth 562.50. Cool. All right, so this is one I really like talking about with my classes each year because it kind of gives you a real perspective on the way exponential growth works. Give me 1 second. I'm going to bring the dog in. Okay, so this is the way the parable of the bacteria in the bottle goes. So suppose you place a single bacterium in a bottle at 11 a.m. and it grows, and at 11:01 it divides into 2 bacteria, so it's doubled its population. these 2 bacteria each grow, and at 1102, they divide into 4 bacteria, which grow, and at 1103, divide into 8 bacteria, and so on. Now suppose the bacteria continue to double every minute, and the bottle is full at noon, or at midnight. The number of bacteria at this point must be 2 to the 60th, because they doubled every minute for 60 minutes. But the important fact is that we have a bacterial disaster on our hands, because the bacteria have filled the bottle, and the entire bacterial colony is doomed. Question 1. The disaster occurred because the bottle was completely full at 12 o'clock. When was the bottle half full? And so here, a lot of students like to go, well, that must be 11:30, right? But in fact, that's wrong. It's doubling every minute. So that means that if the bottle is full at 12, it was half full at 11:59, just 1 minute before the disaster. Okay. So suppose that you're a mathematically sophisticated bacterium, and at 11:56 you recognize the impending disaster. You immediately jump on your soapbox and warn that unless your fellow bacteria slow their growth dramatically, the end is just 4 minutes away. Will anyone believe you? All right, and so the answer to this one is going to be not likely. And the reason being, right? So let's just break it down this way. At 11:59, the bottle was half full. That means at 11:58, the bottle is a quarter full. That means at 11:57, the bottle is an eighth full. And at 11:56, the bottle is a 16th full. So for these bacterium's entire life, which has been 56 minutes in this bottle, the bottle's never even close to full. It's only a 16th full in their entire lives. It's been even less full than that. And you're telling them that all of a sudden, in 4 minutes, which is a relatively short amount of time compared to the rest of their lifespan, all of a sudden the bottle's going to be full? Probably nobody believes you. All right, it's 11:59, and with the bottle half full, your fellow bacteria are finally taking your warning seriously. They quickly start a space program, sending little bacterial spaceships out into the lab in search of new bottles. Thankfully, they discover 3 more bottles. Working quickly, they initiate a mass migration by packing bacteria onto the spaceships and sending them to the new bottles. They even successfully distribute the population evenly among the 4 bottles, just in time to avert disaster. How much time have they gained for civilization? So, you've effectively quadrupled your living space. But the problem is, think of it this way. At 12, there's 1 full bottle. That means at 12:01, the bacteria are going to double again. So you're going to be filling 2 bottles. And at 12:01. And at 12:02, the population doubles again, and it's going to fill 4 bottles. So you've effectively bought yourself 2 minutes of living time. And so this is just to illustrate, if you continue this process, in about 5 hours, if we estimate a bacteria, let's say a bacteria takes up about 1 cubic millimeter of space, in about 5 hours, this would fill the known universe. So this is just to illustrate that exponential growth is not sustainable. So exponential growth leads to repeated doublings. With each doubling, the amount of increase is approximately equal to the sum of all preceding doublings. And the other thing is exponential growth cannot continue indefinitely. After only a relative small number of doublings, exponentially growing quantities reach impossible proportions, as we illustrated with the parable of the bacteria in the bottle. So I know it's a scary time, but all these exponential curves that you're seeing are eventually going to flatten out and become logistic because exponential growth isn't sustainable. We're just trying to get them to flatten out earlier rather than later. Okay, guys, stay safe. Talk to you soon.